This is sort of a workshop. It was meant to be a workshop, but due to some communication issues, this is more of a talk. But hopefully this is still going to be quite interactive at the end, so we will have a healthy discussion about blockchain technology in the end. So what this workshop / talk is going to be about is the usability and security and privacy limits of blockchain technology. And first thing about myself, I'm Joris, I'm a software architect at a Jibe company. I'm from Eindhoven, Netherlands, just like Jibe company itself. I'm a free software enthusiast, so you won't see me running anything I can't compile myself. I'm all about digital rights. I will defend your digital rights until my dying breath. And my pet peeves are operational and mostly information security. So that's where the blockchain comes in. This is a very interesting topic to me. So our goals for today is to get to know what blockchain actually means, because you read a lot about blockchain in the media, and many blog posts talk about blockchain in some of in a very vague manner, and it's like this magic technology that solves everything. But at the end of this talk, I want you to have a good fundamental idea what blockchain actually is and what it does and what it doesn't do. So then you know what its strengths are, what its weaknesses are, and when to use it and when not to use it, right? So this is a very big disclaimer. I couldn't get a bigger font than this. This presentation is full of opinion. This opinion is of myself, it's not the opinion of my employer, not the opinion of our customers. So anytime I express an opinion, please bear that in mind, right? So, the agenda for today, first we'll go over the blockchain 101, so I'll explain what blockchain is, how it works, what it does. Then we have a case study, that's a project in which blockchain is used, and then we'll go over the blockchain applicability, and after that we might have an interesting discussion. So if you have any questions, please save them for later so we can have an interesting discussion at the end. So first the blockchain 101, right? This is going to be a very quick, high-level overview, so I will skip many interesting but boring technical details. So at the end of this overview, you can't build your own blockchain yet, but you have an idea of what the concept does. So before we get into blockchain, we first have to introduce you to the concept of distributed systems. If you're not already familiar to distributed systems, a blockchain is a distributed system. And so a distributed system, this is the official definition of a distributed system. I copy-pasted from Wikipedia. And of course, a distributed system is a system whose components are located on different network computers, which communicate and coordinate directions, passing messages to one another. So this is a bit vague, right? The internet is a distributed system. Everything basically is a distributed system nowadays. There are distributed systems in my laptop, so it's a bit too vague. So to make it a little bit more comprehensible, this is my own personal distributed system definition. That narrows it down a little bit. So in this case, a working distributed system we're talking about is a state machine. A distributed state machine, a network running on different machines with consensus about the state. So what that means is that every computer on the distributed state machine has the same idea of what the current state of the state machine is. And the state machine itself is shared across all nodes. So if you think about this, this is a problem that comes back all the time. Every time you make something out of more servers, you run into this problem. So quickly, a state transition function. This is just a very, very simplified version. We will come back to the state transition function many times, so keep this picture in mind. So you have a state. The state can be anything, can be a number, can be a database. You have a function that operates on that state based on a certain input. And based on that input, it creates a new version of the state. So, and it keeps on going like that, right? This is a state machine. So, and a distributed system is basically just like this. This is a very, very, very simplified version of a distributed system, but basically we can start reasoning about distributed systems from this image. So in this case, 6 computers all connected to each other with a little cable, and every computer has its own state. So in this case, the state, to make it simple, is just a number. So all the computers are now in consensus, everyone knows that the state is 1, everything's fine. And this is the most ideal approach, right? So if we have a distributed systems across multiple machines, you just run a wire between every single machine and everyone can communicate with each other, that's fine. So this is the initial idea of a distributed system. So when the state changes on one machine, it can just directly communicate with every single other machine and says, okay, my new state is 2, everyone has the new state, and so we have reached consensus, right? So this is a working distributed state machine, but it has a few downsides. So every computer now is connected to every other computer with a physical cable, even though cable companies would really like that to happen all the time. That doesn't really work, especially not across the globe. We can't have a full mesh. So it won't scale very well, right? So it's expensive and we can't do that. So in reality, distributed systems are more like this, right? So not every computer is connected to everything else, because why would you? You can just route messages through the network, everyone can cooperate, so they can still communicate with each other, but not directly. This solves the problem of having to run cables everywhere. This is more of an idea of how the internet works. So it still works, right? So you can still update the state of one computer, distribute it across the network, although this time it goes in little steps. So that first those machines get updated, they propagate it through the network, and everyone has the new state, and we have consensus again. So this state machine works without pulling cable everywhere. It still has problems. This is a lot better, but we have issues, and we have no failures, right? So computers are not connected to each other all the time, so computers might fail, and that's all sorts of reasons. Network interference, hardware failure, software failure, in one unbreaking computer, etc. It all happens, right? So we have to make sure that even if a node fails, everything still keeps on working. I remember these things, the ISM net splits, these are exactly node failures, right? So a node in the middle somewhere fails and the entire IC network splits in half. So we want to have a recovery mechanism, right? So what if this happens? So one computer is gone and the other computer can't fit to the network anymore, there's no communication, there's a network split going on. So now if the state is updated, it's broadcasted through the entire network that is still connected. So then the state is broadcasted. We have consensus on the left part of the network, but the right part of the network is not part of the consensus because the connection was lost. So when that happens, the computer comes back, and now what? Now we have consensus on the left, the network is restored, but now we don't have consensus across the entire network, so the state machine fails. So this is not fault tolerant. So this is the terminology we use to describe how tolerant to faults a distributed system is. So this system with the node failures is not fault tolerant. The most ideal approach to fix this is to keep a transaction log. You probably recognize a transaction log from databases. This is the same idea. So we keep a sequential log of all transactions that happened on the network. And so when someone reconnects to the network, you just replay the log and everyone catches up to the state and we don't lose anything, right? So a log looks like this, right? So you have step 1, step 2, step 3, and set the value. So these are all the inputs of the state transition function, and we keep on replaying the log every time we reconnect. So in this case, we have a transaction log, and we keep an index of where in the log we are. We have a reconnect event. Everyone on the left is on step number 2, everyone on the right is on step number 1. So then when we reconnect, we have figured out, wait, I'm probably behind. I'll ask my neighbor at what step they are. They are at 2, we're at 1, so what's the next step to do? It's 2, we have consensus again. So now we have sort of fixed the issue of node failures, and we can reconnect to the network and replay the log, right? So this looks like a very nice solution until you start thinking about other problems. So what if this happens? We are all on the same state, everyone has a transaction log, we lose a machine, happens, So now what? Now we have two machines updating the state, because on the left everyone's connected to each other and one updates the state, and on the right everyone's connected, it's just the one updates the state as well to a different one. Now we have two transaction logs, everyone gets propagated again. Now we have no consensus, right? So even though the left side and the right side of the network think they have consensus with all of their neighbors, in reality it's not always the case. So when the connection comes back, we have a problem, right? So now we can ask our neighbor, what is step number 2? Is it 3 or is it 2? Now we have a conflict. We have lost consensus on the network. So the entire distributed state machine crashes and burns, and we have a problem. So no, this is happening on that one node that comes back. So we have 2 times step 2, and which one is it, right? So now we have an issue on the network. And the solution to this is to introduce a master node. So you have to have a choice. What node in the network gets to choose the right order and validity of transactions. So all of these inputs of the state transaction function need to be validated and executed in the right order. And so one node, or out of the entire network, gets to choose whether that should execute or not. So then it does this, for instance. So it says, the value to 3 is not right. We can use value 2 and ignore value 3 because that one node was not thinking straight. So then you have the problem of who gets to be the master, right? So everyone in the distributed system is equal. So you have to select the master somehow. And there are many, many ways to do that, but they all boil down to basically this. You have a distributed network like this, and if you think about it, everyone's still basically connected to each other, right? So everyone can still communicate with each other, even though it's not directly, but for all intents and purposes, everyone can send messages to everyone else. So you can broadcast things over the network. So what you then can do is just play a little game. You could say, well, this is a very, very oversimplified version of master selection, but you can, for instance, just roll a dice, and whoever has the highest number rolls the dice, is the master. If there's a conflict, those two roll the dice again, eventually you have one master, right? It is a very simple version of master selection. We also want to look at network connectivity and stuff like that, but in practice, well, that's basically it. So in this case, you know, someone wins, one person wins, then you are the master now. So that node gets to decide if there's a conflict, who gets to win, right? So then we have consensus on the network again. So to recap this little 101 of distributed systems, we need a partial mesh broadcast because we can't connect every single computer to everyone else. We need a transaction log for restoring transactions when we lose connection to the rest of the network. And we need a master node to fix conflicts when network splits happen. Right? So, it works, but we still have problems. And these problems are that everyone has to play by the rules. So, for instance, the master selection, everyone has to play by the rules. You can't just say, well, I'm going to rule 6 all the time, and everyone has to believe me. So if not everyone plays by the rules, the network still fails. We still have a problem. So what we have achieved here is crash fault tolerance. If everyone plays by the rules, if everyone is behaving nicely, then with node crashes, we can recover from that. We still have consensus on the network, we still have a distributed system that works. But what if someone doesn't play by the rules? So, by the way, this consensus algorithm then CFT, right? So crash fault tolerance. If you ever see that term, now you know what it means. There are a few interesting implementations of crash fault tolerance. Paxos is the old one. That one has been around since 1989. If you like reading lots of complicated stuff, read that paper. If you write a distributed system right now and would like to read an interesting paper that is actually easy to read Raft. Raft is a much better solution that does the same thing, but at least that one is easy to understand. Right, so What we not have achieved yet is Byzantine fault tolerance. So what if not everyone plays by the rules? And Byzantine fault tolerance takes its name from the Byzantine generals problem. I won't explain the generals problem, by the way, because there's a Wikipedia page about it, but what it boils down to is you can't trust anyone. So if you can't trust anyone, how can you still have a distributed system? How can you still remain your consensus in your distributed system? So that means that we can't trust all the messages we receive. We can't trust any other node. We can't make any assumptions about the trustworthiness of anything we receive. But we still want to reach consensus, and we still want to remain crash fault tolerant. So it's a superset of crash fault tolerance, right? So this is exactly where blockchain comes in. This is the niche problem area where blockchain shines. So for this talk, let's focus on Bitcoin for now, because Bitcoin is the first large-scale blockchain network that is actually running in production, and it's still running. And it introduced some interesting concepts that make blockchain technology tick. And so you can say that Bitcoin is a Byzantine fault-tolerant distributed state machine. That's basically all it is. It's nothing more, it's nothing less, it's exactly that. And what it does is, so in this case it's PFT, right? So that's the term we use for that. What it does is it has several steps. And I'll guide you through all of the steps, and at the end you have an idea of how this algorithm works to reach consensus over a network, even though you can't trust anyone. So first step is identity. Because you can't trust anyone, you still have to identify who you are communicating with. So you need some form of validating who it is you're talking to. And for that we use public key cryptography. It's everyone has a private public key pair. So you recognize this out of SSH and TLS, and so this is just this is existing technology. It's nothing new, but it's ideal to identify people. Everyone on the network is identified with a public key. So as the name says, of course you have a public key. It's public. Everyone knows you by that. And from now on, you can see this as an address. So where Bitcoin is used to send money back and forth. So if you want to send money from point A to point B, you send money to an address. And this is basically just that public key. And of course, you have to keep your private key safe. Your private key is your identity. If you lose your private key, whoever has your private key can use your identity. This is exactly how cryptocurrencies are stolen. People steal someone's private key or trick someone into making a transaction they don't want to, but basically that's it. This is what people call our wallet. It's just a private key. So it's important to remember that a public key is just a random 256-bit integer. It's not completely random, of course. It's a little bit of a curved key, but it's a pseudonym. It's not anonymous. It's one of the main talking points about blockchain technology. Right? People keep on claiming it's fully anonymous. It isn't. It's a pseudonym. So you have to do everything out of the same identity, and if you track all of the spending behavior of that identity, you can still sort of figure out who you are. It's important here to keep in mind we are working with pseudonyms, and it's not anonymous. So what you can do with a public key and a private key is, quick recap, you can just verify signatures made using the corresponding private key, right? So if I have a piece of data and I create a signature on it, only I can create the signature because I have access to the private key, and everyone else can verify that that signature is correct. So that verifies both the payload and it verifies the identity of the person who made it. And so the first thing we do with that private key is sign the input of the state transition function. So every time we want to change something on a network, we want to broadcast something over the state transition function, we sign the input so everyone on the network knows who did it, right? It's really simple. So remember the state transition function, we sign the input. So we know that someone on the network with that pseudonym wants to change the state based on the input of the function. This is an oversimplification, but for the explanation of how Bitcoin works, this is basically the state. We have Bob's address, Alice's address, and Eve's address as keys, and the values are how many Bitcoins they have. Bob and Alice have a normal amount of Bitcoins, and Eve is rich because Eve is evil, right? So, and the transaction itself is really simple, right? So we know who made the transaction, so we always know who wants to move money around. So the transaction in this case would be 1 Bitcoin, for instance, from me to Bob's address. So it's really simple with that. And the state transaction function is just pumping Bitcoins around. So it says, well, the input is how much and to where. Those are just 2 parameters of the state transition function, and that's it. The next step we would do is transaction verification. So, as you remember, the distributed system is a system on which every node can communicate with every other node. So we broadcast this to every other node, and every other node can receive this and verify it. This is an immutable append-only data structure because blocks can only grow, and you cannot change any values in the blocks in the past. So this data structure is made in such a way that it's everything that happened in the past you can't overwrite again. And it's append-only. So you can't just update values in the past because, of course, those hashes need to be updated again, and you have to propagate that change over the entire chain. So it has a few interesting benefits, and this is to solve the replayability, basically, of all of the states. Because if the state becomes malleable and the state transaction becomes malleable, you cannot have a trusted source of information about what the transactions would be to get to the current state. So if you reconnect to the network, you just have to re-execute all of those transactions to get to the current state, right? But then we have the same problem again. We have to select who the master is, because this is still a distributed network and someone has to add the block to the chain. But only one node can add the block to the chain, because if other nodes do that and they have the transactions in a different order, they might have missed some transactions, or possible, then this block becomes different. And if that block is different, the hash is different, and so the chains across the network are all different. So to keep the network sane, the easiest way to do that is just to make one node the master and create a new block to add to the network for everyone else. And what Bitcoin introduced here is the proof of work consensus algorithm. And what this does, it introduces a very, very computational intensive puzzle that is really hard to solve, but it's really easy to verify whether the answer of that puzzle is correct. It's a little bit more complicated than this, but for all intents and purposes of this talk, this should suffice. And on average, only one node comes up with the correct answer every 10 minutes. So the puzzle is made in such a way that on average only one node in the entire network, based on the computational power of the entire network, that only one node can come up with the right answer every 10 minutes. And so when the network grows, this puzzle becomes more and more difficult, and it also corrects basically based on the amount of computational power available. And so this node that wins this puzzle gets rewarded in Bitcoin. So if you win the puzzle, you can write an extra transaction at the end of the block saying, oh, and by the way, I get another Bitcoin out of nowhere. And if everyone agrees about those rules, sure, that works, and it's verifiable, right? So we don't have to trust anyone. We only have to trust that someone can come up with an answer to a puzzle that only one person can come up with, and we can easily verify that. So then, even though we don't have to trust the node, we can verify whether the node is lying or not. So, yeah. So it has a number of interesting benefits. So we fairly select the master node each iteration of the blockchain. So every time a block needs to be added to the blockchain, so every 10 minutes, we fairly select who can do that. Of course, the algorithm is made in such a way that if you, it's not possible that one node gets to be lucky and create 10 blocks in a row, because that would be unfair, right? So you get fairly rewarded based on the amount of computational effort you put into the network. So if you calculate long enough, eventually you will be the winner and you will get a Bitcoin. Well, again, it's an oversimplification, but that's basically how it works. And it protects against denial of service, because this forces the entire network to work in lockstep. So every 10 minutes there's one block. There's no way around it. No one can all of a sudden magically appear and have lots more computational efficiency. You cannot just spam the network with new blocks, because there's only one node that is physically capable of coming up with this new block. And an important part of this, it incentivizes the stewardship of the network, because these nodes that do these computations, that keep on the network working, they have to do a lot of computation, and it's not free, of course. I mean, it requires your PC to be on all the time, and you need to have it running on 100% CPU power all the time. So it's a bit of it's work to keep the network going. So by giving an award, a reward for this stewardship for mining, people get incentivized to donate their computer power to it. At this moment, for Bitcoin, that is a job in itself. You have specialized hardware for it, etc. But still, it becomes economically viable to donate your computer power for the good of the network. And so this has allowed the Bitcoin network to grow as much. But of course, it has some downsides. Since we have a transaction block every 10 minutes, you actually have to wait up to 10 minutes before your transaction is actually verified and propagated across the network. So if we look at this as a normal distributed system, a transaction finality of 10 minutes might be a bit slow, right? And of course, there's a huge amount of power abused. At the moment, I think Bitcoin uses as much as a few small countries combined. So it's the opposite of green technology for the good of Byzantine fault tolerance. So it's a bit of a debate whether or not this is something we should continue doing. But good, it works, and it's the only good solution we have, sort of, but yeah. And then step 6 is that the puzzle winner, the one that created the block, distributes this block across the network, and everyone gets the block and can add it to the chain. So when you receive this block, you can easily verify the block, because as I said, the puzzle answer is easy to verify but hard to get to. So every node can verify the puzzle answer. If the puzzle answer doesn't make sense, discard the block because it's probably spam. You verify the transactions. So when collecting transactions, you can verify them, but then when you add the block, you can verify them again, just to make sure that that one node that has added the block is, even though it won the match, still isn't lying about things. So you can verify the transactions and make sure that all of the signatures are correct, so that one node is still not capable of stealing people's money. And you have to make sure, of course, that the money is actually there to be sent. So it's the same transaction verification again. And so every node, now when the block is verified, the block is added to the chain, you can execute all the transactions in the block, and you update the state, and you have consensus across the network. So this is basically how that state machine works, and how Byzantine fault tolerance is achieved. So to recap in basic, so first we have the identity step. We make a transaction by making an input of the state transaction function that is broadcasted across the network. You verify that transaction when you receive a transaction. Once you have a collection of transactions and you are a steward of the network, so you are a miner, you create the block and you add your proof of work, so you get to add that single Bitcoin at the end, and you distribute the block across the network, everyone verifies the block again, executes the transactions, and then we go to step 2 again. You have a transaction, and etc., etc., etc. So this is the loop in which the network works. But then we still have that issue of crash fault tolerance, because this solves the Byzantine fault tolerance problem. But now we kind of have the issue of crash fault tolerance. What if half the network can't reach the other half of the network? So we still have to have a solution for that. So for instance, what if, let's for instance say all of the undersea cables between Eurasia and the US get split. Then everyone here in Europe is happily mining and happily adding blocks to the network, and everyone in the US is doing the same, and they have no idea that the network is split, because for all intents and purposes, it might just be that, I don't know, everyone turned off their computers, or all of their moms have unplugged their computers, we don't know. The network keeps on growing, and there's a network split at the moment, just like with IRC, there's a network split. So it keeps on growing and growing and growing. And all of the transactions that are in these tails are all valid, right? So that's a problem. So when money is sent in one tail and money is sent in the other tail, it might become incompatible. You cannot join these things because these are immutable. They are append only. So you cannot solve this. You cannot just do an easy merge or anything. So what we do then is very rigorous. Just say, well, sorry, one chain. All of your transactions are now invalid. Roll back all of those transactions because you lost. And the way that's determined is basically just see what the longest chain is, and the shortest chain, when the two networks get reconnected again, they are validated. So it's really easy to verify again, right? So you receive lots of blocks. When the network reconnects, you connect all of those blocks to the parent block where the hash points to, and then you can easily detect, oh wait, we've got a network split, measure the two lengths, and destroy the shortest one. And before you do that, you roll back all of the transactions on your state and start from there on. So, yeah, so now we have achieved crash fault tolerance, and everyone can be in consensus again when the network rejoins. And that's one important part about smart contracts. Bitcoin doesn't really have those, but a smart contract is one of those marketing terms that you hear everywhere. It's a solution to everything, and every distributed problem can have a smart contract, and now you have a solution, right? So what are those anyway? So it's actually really, really simple. A smart contract is just a user configurable state transition function. So you can see it as a meta state transition function. So what if you make your network state transition function, the original one, also accept new state transition functions in a transaction? So then you can program the state transition function to accept new code. So like you can accept new state transition function. So when you have a transaction in your block, you can also say, well, I want to call this function that has been distributed in this transition. So you give those functions an address, and you have to identify somehow that this function can do something. So for instance, in Ethereum, these state transition functions have their own address, and you can actually send them money, and they do something with it. Usually that's very useful for things like money laundering and stuff, but the idea is that the blockchain network becomes more malleable, it becomes more programmable. You can add more functionality to it. So then you can create your own state. So for instance, in Bitcoin you have a very simple state, like this person has this much, this person has this much. If you make it more malleable and you make it an actual sort of key value store, sort of database, you can do all sorts of things. You can keep track of how many transactions have been happening, you can apply rules to it, you can make some access control, all sorts of really cool stuff. So you can, for instance, make an entire autonomous company. Someone tried that, it didn't go well, This makes a blockchain technology a little bit more useful for ordinary problems, right? So in the end, a smart contract is just a user configurable state transition function. So to bring this back together, so a blockchain is a distributed state machine. It's Byzantine fault tolerant, so we don't have to trust everyone. It has an immutable transaction history, so all the transactions in history cannot be overwritten, cannot be changed. And the transactions and state of the state transition, they're all shared across all nodes. So all nodes have a full view of every single transaction. It has a few downsides. It has pseudonyms, so it's not anonymous. It's completely transparent. It's relatively slow and relatively expensive. Of course, there are solutions to all of these points, but this is the basic blockchain idea, right? So if you have a distributed system and you need Byzantine fault tolerance, this is what you need to make sure that you know this is how blockchain works. To introduce an idea of why you could also use blockchain just for other things apart from just pumping money around, I'll introduce a case study. And this case study introduces the project of Poseidon. Poseidon is a project created, let's see, I think 2 years ago now. And it's quite an interesting project. Poseidon stands for the protection and control of secured information by means of a privacy-enhanced dashboard. I didn't come up with this, but that's what it means. The idea of Poseidon is it gives organizations the means to comply with the GDPR. I mean, that's cool, right? And it gives users the means to exercise the GDPR and the right rights. So this is quite a lofty goal. So the GDPR is a very, very important piece of legislation, and it impacts all of us. So if we can solve that with software, that would be cool, right? So before we can dive into how we do that, I'll go over the GDPR in a nutshell. So an organization can only ask for personal information if you really, really need it. So you can't just ask anyone for all of the information if you don't need it. That's absolutely illegal. So I don't know, if you are selling a house, for instance, you cannot ask for someone's sexual preference, because that has nothing to do with what kind of house you're buying. And you have to explain why you need the information and what you intend to do with it. So if you collect information and you collect someone's email address, you have to explain, I need your email address because I need to send you a login code, stuff like that. You have to be very, very transparent about that. And before you collect that information, this is important before, not afterwards, you have to get explicit permission of the person you get the information from that is actually okay. So you have to be transparent in what you collect, why, and you have to have explicit permission. And you have to keep all personal information secure at all times. And this is important. I mean, personal information can hurt you, right? So if it becomes public, especially really sensitive personal information, that is painful. That can cost you your career, your life. Rightfully, the European Union has put fines on breaches of this security line. So if you are collecting personal information and you don't have your security up to snuff and it leaks, then you will get a huge fine. I mean, this fine is one of the largest fines the European Union has ever dreamt of. I mean, their fine is calculated as a percentage of your turnover, profit per turnover. So if you are a low profit margin company, this can completely end you. So lots of companies are they're afraid of the GDPR. They see this as a threat to their existence. So that's why you now see lots of GDPR related stuff popping up, because companies really want to invest in making sure they are compliant, otherwise it's going to cost them their livelihood. So once you have everything safe, you still have to be transparent about what information you have on someone. So if I go to any company, I can ask what information you have on me, they have to tell me. And if you don't need that information anymore, you have to delete it. You have to remove it, because there's no reason to keep your information, of ordinary citizens, if well, just hoarding it. There's no reason for it. And you, of course, have to make it possible to move information to a competitor. Because the European Union is all about investing in the open market and making sure competition keeps on happening. So if a company sits on a bunch of personal information and says, well, yeah, if you want to move to a competitor, you have to fill out all those forms again, you have to go through the same process. Lots of people don't want that. So it's stifling innovation and stifling the possibility for new companies to pop up in an existing market. So this is a rule to make sure that there's more competition going on. And from the user point of view, of course, it's really nice to have this. You know exactly what organizations have on you, you know what to do with it, why they have it, you know that if they have it, you have given your explicit permission. You can update your information at any time, because if a company has information on you, let's say your address, and you move, then it would be nice that you have the means to update that address. Because otherwise, for instance, invoices get sent to the wrong address and then you get in financial trouble. So you should be able to update all information that companies have on you. You can request deletion of your information at any time. So if I deem some organization that I thought was trustworthy, that organization is no longer trustworthy, I can just say to the organization, well, yeah, I don't trust you anymore, delete all my information. Since every organization, that's why the asterisk is for, since every organization has to be GDPR compliant, including the governments, you cannot just always do that. So, for instance, the tax agency needs to be GDPR compliant. I wish I could tell them, forget about me, but I can't, because they still try to get money from me. Anyway, so, but you can move information to a competitor if you don't trust them. So, yeah. But there are no competitors for the tax agency. Right, so Poseidon tries to solve all of this for you. So this is the official marketing blog from the website. So it will develop and deliver an innovative, intrinsically scalable platform. That sounds cool, right? So it scales really, really well. And as an integrated and comprehensive solution aimed to safeguard the rights of data subjects. So this part is important. So it's an integrated solution that first and foremost safeguards your rights. It's not for organizations, it's for you. So this is put into the market to safeguard the rights of you and I. Data subjects are ordinary citizens in this case. And we exploit cutting edge technologies like smart contracts and blockchain because that adds security, right? And as well as an afterthought, we will also support organizations in management and processing while ensuring GDPR compliance. So it also helps organizations to be compliant with the GDPR. But first and foremost is to safeguard your rights. This is funded by Horizon 2020, which is a project by the European Commission to invest money into innovative projects that help along the European Union and to make sure that the European Union stays competitive against the US and China, etc. And it works. We don't do that by ourselves. We have a whole team of interesting companies and organizations in our consortium. So ourselves, of course, Jibe work on this. Accenture, the large company. We all heard of that. The city of Santander is interested in this because also smaller cities need to be completely GDPR compliant. Tecnalia is working on this, which is a large research organization from Spain. The Italian Ministry of Finance is interested. So as I said, the tax agency needs to be GDPR compliant, but has a lot of rules. So we have to make it easy for them to be GDPR compliant. Softly is a software house from France, making mostly software for governments. The University of Coimbra does lots of research and is the brains of the operation. And we have the Malta Information Technology Agency, which is the central IT agency of the Maltese government, so the entire Maltese government is on board. PNO does consultancy for us, and we have ELAX, which is a large team of lawyers to explain to us what the GDPR actually means, because even though I gave you a short overview, it has a few more intricacies and important details that we cannot forget. Right, so we have a website, you can visit it if you like. So what we envision for the Poseidon platform is to create a one-stop shop for all personal information. So there is one thing in the cloud somewhere, always available, where everyone is connected to. So every user, so that means every data subject is connected to this. Every organization in the entire European Union is connected to this. And it gives us some really interesting and useful features. So we can make sure that personal information is transacted between organizations in a secure and well-informed manner. So we have a way of policing sort of the transaction of personal information between organizations. And it gives us the opportunity to, with software, ensure GDPR compliance. So organizations can now exchange information amongst each other and ask for information from data subjects and make sure that there's explicit consent for that. And so it sort of works as a sort of a traffic call, like yes, you can go through and no, this can't go through. And so it's quite a large undertaking to make sure that this works for the entire European Union. So once this eventually works, the GDPR becomes a matter of installing a piece of software and you're compliant. So we have quite a few challenges for this, of course. So there are accessibility challenges, security challenges, scalability challenges, because this is large, you know. The ease of use challenge is a very important one, and of course all these budgetary challenges. So I'll walk through these one by one and give you an idea of how we tend to solve these problems. Of course, there's the accessibility challenge. It needs to be accessible to all European citizens, including your grandparents. So it's completely regardless of technological literacy. So you cannot expect people to be really good with computers, even though we use blockchain underneath. Nobody needs to know what blockchain actually is, right? Nobody expects everyone to attend this talk, so, right. And if you have disabilities, that shouldn't matter. You should still be able to use this platform. So if you are blind or you cannot use an ordinary laptop, it should still be accessible. And we can't expect everyone to have a smartphone, we can't expect everyone to have a superhuman device or anything, so it needs to be accessible for every European citizen who has access to the internet. So what we come up with is make it web-based, right? So there's a dashboard, a website, literally just a website for every data subject where we can exercise our GDPR derived rights. So everyone can use it. Web-based technology is still the most advanced when it comes to accessibility. It's the most accessible. Everyone who has internet access can probably open the website, right? And then we have the security issue, because this network, this central thing, will eventually, hopefully, take care of all of the personal information transactions in the European Union. So we need to make sure that this is super secure, right? So we can't just make some assumptions or something, that this needs to be absolutely strongly secure. So the first thing we use is strong authentication. I mean, we need to make sure that whoever is acting as a data subject can prove that they are actually themselves. So we use EIDS, which is a European-wide identification network. Every one of you has access to it. If you have a national login, the national login is connected to it. So you can use your national login system to log into the web-based dashboard. We have added strong end-to-end encryption because there's very sensitive information going back and forth between data subjects and organizations, and there's a lot of exchanging going on. And you don't want someone in the middle to be reading along what you're doing. And as this is a very important point. We do not want a central authority with access to all personal information. I mean, imagine that this gateway falls in the wrong hands, right? So we've had trouble in Europe with dictatorships before. We don't want the means for anyone, even in the far future, to abuse this treasure trove of personal information. We need to make sure that everything stays absolutely hidden, even for the administrators of this network. So we cannot add a central repository. So there's no way we can just plunk a database in the middle and say, well, just update every personal bit of information in that big database, and we promise we'll keep it secure. We can't do that. There's no way we can promise the security for as long as this network keeps running. And so we need to facilitate a secure conduits between organizations to transport information. So we can leverage the experience organizations already have in keeping this information secure. We distribute this information across organizations. So we make sure that there's not a central organization with access to everything. Every organization, according to the GDPR, only has access and storage of the information they should have. So if there's a data breach, which happens now and then, not everything gets spilled, just a little bit of that organization. And so we make sure that there's an easy way to exchange information between organizations. And of course, you cannot just exchange information, you have to have explicit consent, and you have to make sure that it's done securely, so we check access permissions without being able to read that information. So there's an issue of scalability, of course. Europe is quite big. And there are many people in Europe and many organizations that want to be GDPR compliant. So we want to scale up from a few hundred users to literally hundreds of millions. And it needs to stay adequately performant. So this network will be bigger than Bitcoin. It needs to be huge to understand the scale of this. I think this is probably the amount of transactions happening like 10 times as big as the largest Bitcoin blockchain network in production at the moment. And it needs to stay adequately performant. So if I give my permission to exchange information, I don't want that to take like, I don't know, half a day to propagate across the network and then eventually that happens. It needs to be completely transparent, right? So it needs to be nice and easy. You say, okay, and the information is broadcasted to the, or is shared with the organization you want to share it with. And of course, it needs to be easy for users to understand and use, and easy for organizations to integrate with. So this takes away all of the friction of introducing this in the European Union, and hopefully make it so easy that it becomes a no-brainer for organizations to do this, because then to achieve GDPR compliance, you just install this and it magically works, right? So that would be cool. Of course, we have a budget. There's a limited time frame. We get about 2 years to come up with something, and of course, the EU gives us a budget, but it's not unlimited. So we also have to make sure that we stay within this time frame and budget. So that means we can use open source software and as much as possible, because then we don't have to write it, right? So we can just use pre-existing open source solutions that have already been verified by smarter people than me. So I can trust that. But to come back to this, it is important to understand that Poseidon is a research project. So we have the task of researching how far we can take blockchain in solving this challenge. Of course, blockchain solves a lot of challenges, but every challenge is unique and every application of blockchain is unique, so we have to make sure that we have a decent understanding of what this actually does. It needs a lot of research to make sure we do this properly. I mean, this solution would solve lots of problems. It would make us all more secure, but we have to make sure we do this the right way. So at the end of the Poseidon project, we have good research results and a proof of concept, but we do not have the actual application yet that runs in the middle of all Europe. So the first idea would be, let's use blockchain and exchange all of the personal information using blockchain. That's an idea. That's not a really good idea, is it? Because blockchain is immutable and blockchain is a shared state. So if we add all personal information on the blockchain, first you cannot remove the information anymore, and all of the information that cannot be removed is shared with everyone. That's exactly the opposite of what we want to achieve. So probably not a great idea. So what if we just encrypt things and put them on the blockchain? Because add some more encryption and make it more secure, right? So also not a great idea, because encryption, even though well intended, will fail over time. Every single encryption algorithm we have will fail in, I don't know, a few decades. If we're lucky, maybe 50 years, but eventually we will find methods to break it, or our computational efficiency becomes much better, so we can break the encryption we have now. So if we broadcast all personal information, even though encrypted to everyone else, someone will keep a copy of that on an old hard drive, and in 100 years from now, if hard drives live that long, can just read that again and say, oh wait, that's that stupid old encryption from 2015, and we can break that now. So then they have access to all of our personal information, so that's awful. Also, blockchain is spend only, and if we exchange the personal information on the blockchain for hundreds of millions of people, that means that the blockchain will grow hugely. I mean, this is terabytes a day, so no one has storage to keep terabytes a day on a disk. So we can't do that. So the only thing left for us to do with this is only exchange permissions over data. So keep the data off the blockchain, because that's not where it belongs. Don't put personal information on the blockchain, guys. And we can exchange permissions instead. So only yes, you can have that, yes, no, you can have that, and put that on the blockchain. So stuff like this, right? So organization A has the right to have info B for user C, organization D, etc. So if we store this on the blockchain, we don't actually exchange any personal information. So then, this is basically what we can do with our blockchain implementation. We can ask for permissions, give them, check them, revoke them, but all of that is just references to information that is available somewhere else. So that means this is exactly where a smart contract comes in, right? So these are functions for the state transition function. So we can make a configurable state transition function that does all of this, and make a smart contract for exactly that permission management. And so, of course, for a state transition function, we have to know what the state is. So this would be our blockchain state. So we have a little table of all the participants in the network. Alice, Bob, and Eva are here again. So in this case, Alice has a request from the bank asking for the passport details, and the bank would like to get the passport details from the government. So this shows you what we can do with this network. So now when Alice says, okay, yes, bank, you can have my passport details, the bank can request these passport details directly from the government. So there's no more need for Alice to go to a scanner and scan that and send a PDF off to the bank, or actually go to the bank and show a passport. The passport details now come from a trusted authority who can say, yes, these are the passport details of Alice. And that transport is done securely and GDPR compliant. So this removes friction for business processes and adds more security, and everyone's happy in the end, right? So for instance, as well, like Bob already gave permission for Tesla to give all their location data to the car insurance. Happens. And Eve, for instance, can go to a hospital, and the hospital is like, yeah, we have to put you under, we have to know what your weight is, can you please give us an idea in advance how much drugs we have to get for you. And so Eve can fill out her weight, and then with explicit permission, the hospital can then buy the right amount of drugs. Right? So we can exchange permissions or personal information using the smart contract. So what happens is then the bank asks for passport details, then you have explicit permission, so that's stored. We have that step before the actual transaction. Then the bank goes to the government, and you can then independently validate whether or not that permission is given, because the blockchain state is shared with everyone, right? And then the copy of Alice's passport is transport secured. Right. But if you paid some attention here, here's a problem, right? So this is the state. The state is shared with everyone, and now everyone can see that Eve is sharing her weight with the hospital. That's personal information, even though it's metadata. We know from Snowden that metadata is maybe even more personal than actual data. This is very, very personal. So what if that hospital is not a normal hospital, but it is, I don't know, a mental institution? I mean, if now insurance companies can look into this and say, well, Eve is going to a mental institution, your health insurance is going up. We don't want that, right? So we have to hide that. Relationships between organizations and data subjects are personal information and potentially very sensitive. So we have to find a way around that. And there are two ways we do this in Poseidon. We use Quorum by JP Chase, which is an Ethereum fork that solves many of these issues, because banking has the same issues, right? They have privacy issues. And we use vulnerable pseudo-identities. As I told you, the identity you have on the blockchain network is a pseudonym, and eventually that can be de-anonymized. So if you use vulnerable pseudo-identities, you use a new pseudonym every time and it becomes more anonymous. So quickly how Quorum works, it is a bit complicated, but what it does, it splits public and private state. So the public state keeps track of all of the household stuff for the blockchain network to work, and you use that as a trust anchor to verify transactions between two parties that have private state. So, for instance, the state that the weight was shared with the hospital is only shared between, for instance, Eve and the hospital. The insurance company has no idea that that transaction even took place. It only sees some trust anchor, which is in this case just a little hash on the main blockchain network, but then nobody knows what that actually means. So we that's basically the main takeaway, right? So we split public and private state, and we do not share private state to everyone. And vulnerable pseudo-identities solve the other issue, right? So we have a list of identities, so a list of addresses for each user, and that list can be infinite, and we keep on using a new address either for every transaction, every hour, every day. It's configurable. And once the user wants to be forgotten, we just throw away the association. And it's no longer traceable that what user has done that transaction, and then it's just a random identity that did some transaction with the hospital, but we have no idea who. In the end, so the Poseidon blockchain network uses only permissions on the blockchain network. We use a permissioned blockchain network, so Quorum is permission, so that makes it impossible for anyone else without permission to connect to the network. You need explicit access first, so that one uses TLS. It uses Quorum to further separate the state. And we use vulnerable pseudo-identities to further protect identities to make sure that even if we start de-anonymizing the pseudonym, we still have no idea who it is. But of course, this is a research project, and so we also can see where there's room for improvement. Firstly, there's a web-based dashboard, and web-based dashboards have a web server, and everyone connects to the same web server, and so hundreds of millions of users use the same cluster of web servers controlled by a central authority. Right? And the central authority is exactly what we don't want with the blockchain network, right? So this creates some friction, and there are several solutions for that, but those solutions are still relatively early, so we are trying to figure out how we can get around the usability problem without introducing, for instance, we can force everyone to install an app, but then not everyone has a smartphone, and we lose like half of the users. We don't want that. So we want to have a web-based dashboard users can trust. So this is still an open issue we are working on. Vulnerable identities. that there is a correlation needed between the vulnerable identity and the actual identity of the user. That correlation can only be destroyed once that user is no longer in the position where they need to verify whether or not they give that permission. But it still means that there is a central authority we have to ask, like, oh yeah, this pseudonym, who was that? So there's still a database somewhere centrally that says all these pseudonyms belong to us. And that's the only way we can make it work. But that central authority needs to be trusted. And so that also goes a bit against the idea of using a blockchain network. Of course, there are solutions for this, and there are solutions on the horizon, but that's still something we are working on. So Untitled is, at the moment, a very capable solution. It's way ahead of any other solution that there is out there now. But there's still, of course, work to do, but it's a huge step in the right direction. The idea of having a central distributed system that takes care of all of the GDPR rights is something we really want in Europe, and something that needs to be introduced in order to safeguard everyone. So, knowing this use case and knowing what blockchain does and can do, we can look at blockchain applicability, right? So if you have a new project and you're thinking of, wait, I want to use blockchain for this, there are a few questions you ask yourself. Is blockchain actually the right solution for this? So there are a few really important things that blockchain introduce to your project, and if any of these questions have no answer, you should probably, look at other solutions, or maybe look at some solutions that work with blockchain but still make it useful. So if you don't have a distributed state machine, then there's no need to use blockchain. If it doesn't need to be crash fault tolerant or Byzantine fault tolerant, don't use blockchain. If it just needs to be crash fault tolerant, I said, you could use Paxos or you can use Craft. But then, if no Byzantine fault tolerance is needed, blockchain doesn't have any added value. And if you don't want shared state on all nodes, then you have to introduce things like quorum to make private state again, and it becomes more complicated. So there are ways around these things, but these are the basic properties of blockchain technology. And also important, are all parties involved capable of running nodes? So every node that is running and has the task of stewardship of the network has is like a central entity, right? So and if every entity with a stake in the security of the project can run a node, then you have the stakes well distributed. But if only a small subset of the entities using this network can run a node, then that small subset has full control over the rest. So then there's no need to be distributed. And you need adequate processing, storage, and network capacity. So if not all of your nodes have that, you should probably not use them. So if you have some IoT devices in the field that can only communicate once every day when a satellite comes over, probably don't use blockchain technology, right? So, and the last one, are you okay with relatively slow transactions? This relatively is important. Because compared to Raft, every blockchain transaction is slow, but if you look at recent innovations in blockchain, they come really close to network speed and transaction time, but still, relatively speaking, they're still slower than something like Raft. So, for Simon, if you ask these questions, there are a few things that we had to solve, right? So we didn't have shared state at all nodes, so we had to come up with a novel solution for that. Not all parties are involved. Not all parties involved can run a node. So take the subjects at the moment can't run a node themselves. So the largest part of the users, hundreds of millions of them, can't run a node themselves. So we need to make that possible somehow. And slow transactions are a problem. I mean, if you go to the Barclays dashboard and you click on OK, you don't want to have one of those spinny wheels for 20 minutes. That's not usable. People will just click away after 7 seconds, so let's not do that. And we have to have some speed increases for that. But all these issues have solutions, but that means you cannot just put blockchain in this drop in place solution. You have to work at it. You have to mold it into something that they actually use. So when the downsides outweigh if the upsides outweigh the downsides, then sure, use it. If not, maybe not. Use the right tool for the job, right? So there are a multitude of possible alternatives to this. So if there's no distributed network at all, you can just use classic authenticated encrypted messages. I mean, we've been doing that since the 70s and it works perfectly well. You have things like distributed multi-party signatures when there's no distributed state machine. You can use zero-knowledge proofs that you just distribute without showing any state. Or you can use like a distributed hash table using homomorphic encryption, and the list goes on and on and on, with possible alternatives to blockchain technology to solve this same issue. But all of them have downsides and upsides again, and every single point of this list is probably another 1.5 hour talk, so I won't do that. So, if you think, oh man, I would like to work on this technology, send us a message because we need help. I mean, this is a massive undertaking, and it's making the EU a better place for everyone. So if you think, oh man, I can really add to this project, send us a message. We're on the Netherlands, I'm here in Push. So both of them have an email address starting with hello, so we're friendly. So if there are any questions about this, or if you are like, oh, I don't agree with that, start a discussion. Sure, this is a workshop. Okay. No questions? Yes.
Could you say a few more words about the logistical? I see you have 2 offices, one here in Cluj, like how many people work here and stuff like that?
We have a team in the Netherlands of, let's see, how many people are there now? 15 or so? And we have an office here in Cluj, which is ever growing, so I lost count. Yeah, so we work together, so it's like a partnership, right? So and that's why I'm here often, and many people out of Cluj are there often. It's just we have 2 offices, and we work in both of the offices sort of equals. So yeah, it's just a spread team, and we keep on making more international contacts. So yeah, that's basically how it works.
Is this an open source project? Or
yes.
Yes.
Yeah, absolutely. So we want to add to the European Union as a whole, as we want to make the European Union more competitive. And so that means we also have to give the technology to our competitors, saying, well, yeah, here it is, go forth and multiply. Because the more companies are involved with this, the better place the European Union becomes to compete with places like the US and China. So yes, everything we do is open source.
Do you have some standardization for the method? For example, if I want to ask, what is the cloud information that companies have on me?
Yeah.
Okay, what is the health information?
Yeah. So we are working on a standardization of identifying pieces of personal information, and every piece of unique personal information has a unique key, and that key we can use in permissions. So there is a big list of, if you want to use, for instance, like first name has a key, last name has a key, etc. So then every line in the state has a unique combination of person, organization, and key of personal information.
So you are creating this metadata, or you are dealing with some data?
We are still looking into what standardized methodology should fit best. So the technology itself we're creating is completely, it doesn't really matter what metadata standard we use, but if there's a metadata standard that solves our issues, we'll just use that. I mean, there are several ISO standards. There's a standard used in many governments in Southern Europe, and there's another standard. So we have to see which one fits best. But that's for this scale of a project, that's an implementation detail we can figure out. But yeah, that's a good point. It needs to be standardized. Yes?
How big of a challenge is availability? So in case the platform doesn't work, won't the company be able to do their job, or people, access institutions and so on?
Yeah, that's true. Yeah, availability is a massive important part. So the more nodes we have in the network, the more available it becomes. So the more organizations add to the network, the more resilient the network becomes. So then, if the network completely fails, yes, all the transactions stop. But we think that a distributed system like this gives us the best tools to ensure availability the best we can. Yes.
From the hardware standpoint, what is a node? Because from my point of view, this is the biggest challenge you're facing. Because if only one organization can run a node, I should put the data on that node, and at that point, the whole thing starts to
Exactly.
stop you.
Proof of work is not the only consensus algorithm we can use. Since this is a private network, we can use different, still Byzantine fault tolerant, but slightly less computationally expensive consensus algorithms. So we can use some variant of proof of stake, for instance, that has a lower transaction time and a lot less computation cost. But yes, the storage and computational overhead of the blockchain network is still something you have to deal with if you want to know.
Basically, can I be a hermit and keep all my data on my personal computer?
Yeah.
And participate as a node, and everybody should ask my machine to share the data. Instead of me providing the data to different nodes.
Yeah, that's also a possibility, technically speaking. But this is exactly where the data subjects come in, the end users. So there are several ways we can do that. We can make software so end users can say, well, no, all of my personal information runs on my own computer, and if you want my information, you can ask for it and get it here. It's here, I know where it physically is. And yeah, so this network does give us the tools to do that. But yeah, that's a really good idea to make it more, make data subjects also participants in the network.
You don't need to have a node in order to do that.
No, there are two ways you can do this. So at the moment, the client of the Poseidon network is just a very simple Python app. So it's literally, you can pip install it, and then you can run it. And if you want to run your own node, this is a permission network, so you have to go through some paperwork. Which can also be automated in the future, but of course you need to get your own certificate and get some verification that you are capable of running a node and not disturbing the network. So we are trying to make the onboarding of organizations as easy as possible.
So what about the transaction fees? So whenever you transfer the licenses for the data, also mention who will pay.
So, since we don't have to use proof of work as a consensus algorithm, we can also make the transaction fees completely zero. Because there is no money thrown back and forth, and the stewards of the network have a different incentive of doing this. They want to be in compliance with the GDPR, and then the incentive question becomes different. So, if I don't want to have a fine, I will donate my storage and network capacity to the network, and I get easy access to personal information and GDPR compliance in return. Does it answer your question?
So if you are an organization, you want to utilize this network, you need to have a node.
You don't necessarily need to have a node. No, you can also connect to this network through one of other nodes that are run by a trusted organization. So, for instance, you can be a large group of small organizations, and together you pool these nodes that you will run a node, and you will use the same node. It's perfectly useful. I guess that answers the question, right? So, thank you all for listening to my very long story, and hopefully we will hear from you, or otherwise. I look forward to seeing you all use the Poseidon platform. Thank you.